Picture a commercial aircraft. Zoom in on its aluminum skin. Those millions of tiny bumps are rivets. Boeing could weld everything together, save hundreds of millions of dollars, and cut production time in half. But they will never do it, and your life depends on this decision. What makes rivets irreplaceable involves a dark chapter in aviation history. In the early days of jet aviation, manufacturers tried welding aircraft structures. The results were explosive decompressions at 40,000 feet. This is Sky Secrets, where we reveal engineering truths. The de Havilland Comet was the first commercial jet airliner. It used welded construction. Within 2 years, multiple comets suffered catastrophic breakups. Investigations discovered that welds created zones where microscopic cracks formed and spread. This tragedy changed aviation forever. Welding is everywhere in modern engineering. Automobiles, cargo ships, skyscrapers, satellites. Every major industry relies on welding to join critical components. The process is fast, economical, and incredibly effective. Yet when you examine any Boeing 787, Airbus A350, or even military aircraft like the F-35, you find something puzzling. Millions of small metallic rivets distributed meticulously across the entire structure. A Boeing 747 contains approximately 2.5 million rivets. An Airbus A380 uses more than 4 million individual fasteners. But why do the most brilliant aerospace engineers on the planet continue trusting this seemingly outdated technology when modern welding exists? The answer goes far beyond simple tradition or manufacturing preference. To understand this apparent contradiction, we must first examine what happens during welding. Welding works by applying intense heat to melt metals and fuse them permanently together. This process creates an extremely strong and durable joint in most applications. That is why we see it everywhere, from the frame of your car to gigantic container ships crossing oceans. But when it comes to aviation, this same technique presents critical problems that could compromise aircraft integrity. And these problems become exponentially more dangerous when you are suspended at 12,000 meters altitude, traveling at 900 kilometers per hour. The first crucial factor is how joints respond to constant vibrations. During a typical 10-hour flight, a commercial aircraft experiences millions of micro-vibrations caused by turbulence, pressure changes, and the operation of jet engines themselves. Think about what happens when you repeatedly bend a metal paperclip back and forth. Eventually it breaks due to material fatigue. Welds, although initially strong, are susceptible to developing microscopic cracks under these constant vibrations. And a microscopic crack can rapidly become a catastrophic failure. But wait, there is something even more alarming about how these cracks propagate that engineers discovered through tragic accidents. Rivets, in contrast, provide a different type of joint. Each rivet acts as a tiny shock absorber that absorbs and distributes these vibrations throughout the entire structure. It is like having millions of small flex points that prevent any stress from concentrating in a single location. This distributed stress system is critical to aircraft longevity. But this is only the beginning of why rivets dominate aviation. The second critical factor involves the materials used in aircraft construction. Modern airplanes are built primarily with ultra-lightweight aluminum alloys, titanium, and composite materials. These materials are selected specifically for their exceptional strength-to-weight ratio. Every gram saved means less fuel consumed during the entire service life of the aircraft. The problem is that these materials present unique challenges for welding. Aluminum, for example, has extremely high thermal conductivity, which means it dissipates heat very quickly. This makes it notoriously difficult to weld correctly. Additionally, when aluminum is heated to the temperatures necessary for welding, its mechanical properties degrade significantly. Here is a startling fact. Aluminum can lose up to 50% of its structural strength in the heat-affected zones during welding. This creates weak points precisely where you need maximum strength. The crystalline structure of the metal changes at the molecular level, introducing brittleness and reduced load-bearing capacity. Composite materials, increasingly used in modern aircraft like the Boeing 787 Dreamliner, simply cannot be welded at all due to their non-metallic nature. These advanced carbon fiber reinforced polymers require completely different joining methods. Rivets, by contrast, allow joining these diverse materials without altering their fundamental properties. No heat, no structural changes, just pure and reliable mechanical joining. The material maintains its factory specifications throughout its service life. The third critical factor is the thickness of materials used in aviation. Did you know that the exterior fuselage of a typical commercial aircraft has a thickness of only 1 to 3 millimeters? It is astonishingly thin, comparable to the thickness of 3 or 4 credit cards stacked together. This ultra-thin design is essential for keeping weight low while providing necessary strength, but it presents a unique challenge for welding. When you attempt to weld such thin materials, the risk of thermal distortion or even burn-through is extremely high. The intense heat can literally burn through the material before a proper joint forms. And here is something most people never consider. At these thicknesses, even slight warping from welding heat can compromise the aerodynamic profile of the aircraft. A distortion of just 2 millimeters across a wing surface can increase drag significantly, affecting fuel efficiency for the entire service life of the airplane. Rivets requiring no heat completely eliminate this risk. They allow precise joining of ultra-thin materials without distorting or damaging them. The drilling and riveting process maintains dimensional accuracy within hundredths of a millimeter. The riveting process itself is fascinating in its precision. First, a hole is drilled slightly larger than the rivet diameter. The rivet is inserted through the opening. Then, through controlled pressure, a second head is formed on the opposite end. This controlled deformation creates an incredibly strong mechanical joint that distributes load evenly. Each rivet is meticulously inspected to guarantee the absence of cracks or voids that could compromise structural integrity. Modern aircraft manufacturers use automated inspection systems, including ultrasonic testing and X-ray analysis, to verify every single rivet installation. This level of quality control would be impossible with welded joints hidden beneath the surface. But here is where the story gets darker. The preference for rivets over welding did not arise by chance or engineering preference. It is written in blood throughout aviation history. In the 1950s, the aviation industry experimented with welded structures in several commercial and military aircraft models. The advantages seemed obvious: reduced production time, fewer joining points, greater efficiency. But catastrophic problems soon emerged. The most notable incident occurred with the Havilland Comet, the world's first commercial jet airliner. This British aircraft was a technological marvel when it entered service in 1952. It promised to revolutionize air travel with its jet-powered speed and high-altitude capability. Several of these aircraft suffered explosive decompressions in mid-flight due to cracks that initiated in welded areas of the fuselage. The crashes were horrific and mysterious. Aircraft would be cruising normally at high altitude, then suddenly disintegrate in mid-air. In January 1954, Comet G-Alep broke apart over the Mediterranean Sea near the island of Elba, killing all 29 passengers and 6 crew members. Just months later, in April, another comet suffered the same fate near Naples, with 35 fatalities. Subsequent investigations revealed that constant vibrations and pressurization-depressurization cycles had caused metal fatigue in the zones affected by welding heat. The microscopic cracks propagated until causing complete catastrophic failures. The square windows combined with welded joints created stress concentration points that eventually failed under repeated pressurization cycles. What the investigators discovered changed aviation engineering forever. The heat-affected zones around welds had different metallurgical properties than the base material. These zones became initiation points for fatigue cracks. Under the repeated stress of pressurization at altitude, these cracks grew until catastrophic failure occurred. This and other incidents led the aviation industry to adopt strict regulations about using welds in critical aircraft structures. Rivets, with their proven safety and reliability track record, became the gold standard for aircraft construction. And they remain so today, more than 70 years later. Let us now examine the specific types of rivets used in modern aviation. Not all rivets are equal, and their selection is critical for structural integrity. Solid shank rivets are the most common and come in several configurations. Round head rivets are used primarily in internal fuselage areas where aerodynamic drag is not a factor. Their design distributes stress evenly around the hole, preventing stress concentration. Countersunk head rivets are used on exterior surfaces where aerodynamics is crucial. They are inserted flush with the surface to maintain a smooth profile that minimizes air resistance. Universal head rivets are a hybrid that combines characteristics of both previous types, offering a balance between stress distribution and aerodynamic profile. Blind rivets, also called pop rivets, are another crucial category. These ingenious devices allow installation from one side only, which is essential in areas where accessing the back of the structure is impossible. The material of rivets is also critical. Depending on their location and function, they can be manufactured from aluminum alloys 2017T4, 2024T4, 7075T6, titanium, stainless steel, or Inconel for high-temperature applications. Correct material selection is essential to prevent galvanic corrosion between the rivet and surrounding structure, a phenomenon that can silently weaken structural integrity over time. Despite the clear advantages of traditional riveting, the aerospace industry never stops innovating. New technologies are beginning to complement or even replace some rivets in specific areas. Friction stir welding is perhaps the most promising innovation. This revolutionary process joins metals without melting them, eliminating many problems associated with traditional welding. The Boeing 787 Dreamliner already uses this technology in specific sections of its structure. By avoiding metal fusion, friction stir welding maintains the mechanical properties of the material practically intact, while providing a continuous and resistant joint. Advanced structural adhesives are also gaining ground. These are not the common glues we know, but high-technology compounds that can withstand extreme loads while adding minimal weight. Many modern aircraft use a hybrid approach: traditional rivets in critical high-stress areas, friction stir welding in specific zones, and structural adhesives as a complement or sealant. But even with these advances, humble rivets continue dominating aircraft construction for one simple reason: their reliability is proven beyond all doubt. Every time you board a commercial aircraft, you are trusting your life to millions of these small engineering marvels, and they perform perfectly, flight after flight, year after year. It is fascinating to observe how the principles that make rivets superior in aviation also apply to other critical structures. The tallest skyscrapers in the world, like the Burj Khalifa in Dubai, use rivets in critical sections where wind vibrations could compromise traditional welds. Large span bridges, like the Golden Gate Bridge in San Francisco, contain millions of rivets that allow them to flex slightly under load without developing structural failure points. Even in naval engineering, deep-water submarines rely on rivets for certain critical joints that must withstand extreme pressures. The main difference is the size and application technique. In these massive structures, rivets can be as large as your fist and are applied through techniques like hot riveting, where the rivet is heated red-hot before placement. As it cools, it contracts, creating an incredibly firm joint. Unlike these applications, aviation primarily uses cold riveting, where no significant heat is applied, thus preserving the critical properties of aerospace materials. The next time you look through an airplane window and see those small bright dots on the wing, remember what you learned today. They are not just rivets. They are the result of decades of research, testing, and tragic accidents that taught engineers painful lessons. They are the reason why commercial aviation is the safest means of transportation ever created. Every single one of those 4 million fasteners on an Airbus A380 exists because welding failed catastrophically in the past. If this video changed how you see aircraft engineering, help us reach more aviation enthusiasts by hitting the like button right now. Subscribe to Sky Secrets because we reveal the hidden science behind flight that most passengers never discover. Activate the notification bell so you never miss our next deep dive into aviation mysteries. What other engineering secrets would you like us to uncover? Drop your suggestions in the comments below. We read every single one.